80. The two extreme materials in this range are air at 1 and water at 80. Everything else is in between. PVC is 4. Dry sand is 5. Rock is 6. Silty soil is 30. And clay soil is 40. So the amount of GPR energy that reflects from an object depends on the contrast between the K of the object and the K of the surrounding soil. The bigger the contrast, the more GPR energy that reflects. That is called the reflectivity. And here's the formula for calculating it. But let's look at some examples related to utilities. Let's start with an easy one. Water saturated sand with a K of 25 going to metal. For example, a metal cable buried in the subsurface. Metal has an infinite dielectric permittivity. So when you do the math from the formula, it has a 100% reflection coefficient, or reflectivity. This means that 100% of the GPR energy that hits a metal object reflects, and none of the energy transmits through the metal. This is the reason why metal objects are the easiest objects to detect with GPR, as this example shows. Now, let's talk about GPR detecting non-metallic utilities, such as PVC and concrete pipes. Say we have a concrete pipe with a K of 4.5 buried in a dry sand with a K of 5. Even before we do the math, you can see that there's not much contrast, so we can predict that the reflectivity is going to be small. Sure enough, when you do the math from the formula on the last slide, the reflectivity in that situation is 2%. Only 2% of the GPR energy that hits the concrete pipe reflects back to the surface, and 98% of the energy transmits through. A PVC pipe in dry sand is not much better. A PVC pipe with a K of 4 buried in a dry sand with a K of 5 gives us a reflectivity of 6%. With such low reflectivity, how does GPR ever find non-metallic utilities? The assumption that most people make is that GPR detects the plastic, PVC, concrete, fiberglass, or whatever the pipe is made of. Well, the reflection from a non-metallic pipe does not only come from the pipe itself. It comes from the material inside the pipe. In fact, most of it comes from the material inside the pipe. That is where the contrast comes from. So with that knowledge, let's look at the numbers again. Let's say that there's air inside our concrete or our PVC pipe. Air has a K of 1. If the dry sand has a K of 5, that's the soil around it, and the air inside the pipe has a K of 1, this gives us a reflectivity of 38%. Way more energy reflecting back to the GPR receiver on the surface. Way more detectable. Here you see reality. Here you see the theory and the reality. One hyperbola has a significantly stronger response than the other. Since they're at the same depth in the same soil, one explanation for the difference in the reflectivity is the target material. One interpretation may be that it's a metal target on the left and a non-metal target on the right. Okay, let's add water to that dry sand and make it wet sand. So now our air-filled, non-metallic pipe is surrounded by wet sand. What does that do to the amount of energy that reflects from the pipe? The contrast between wet sand and air is larger than between dry sand and air. So more energy reflects in the wet sand situation. 66% versus 38% in the dry sand situation. That means that a non-metallic air-filled pipe is easier to detect in a wet sand than a dry sand. How many of you have heard somebody say, "I could not do the GPR survey because it rained"? Or, The GPR survey